Hey guys, in this video we are going to discuss Taylor series method. We are going to solve this initial value problem using Taylor series method, right? Suppose you have a first order differential equation. This is a first order with the initial condition, right? So we are going to solve this numerically. Suppose this one is pretty complicated to get an analytical solution, or we cannot obtain exact solutions, right? Let's assume that, right? Now we are going to solve this initial value problem. This is called initial value problem, right? So we are going to solve this initial value problem using Taylor series method, right? So suppose this is your initial value, and so x is the unknown function, but we know the value of x at x naught, which is equal to x naught, right? Value of x at t naught, so t naught, the unknown function x naught evaluated at t naught is equal to x naught, right? So we only know that point. So we are going to find x, the function x, unknown function x, by solving this numerical, right? So first step, you had to define the grid. So our independent variable is t, right? So this is your t axis, right? We start off with this point t naught, let's discretize this. This is your t1. Alright, second. Yep, this is your t1 and t2 and so on, right? And let's assume the gap between any two consecutive points is h, right? So we start off with this t naught, right? And let's consider this point t1, the very next to this point, the very neighbor. Yep. So t1 is equal to t naught plus h, right? And x1 is the approximation to this. So x of t1 is the exact value, right, which is this x of t naught plus h. So this one is the exact value. This is your exact value of x, function x at t1. So this one is the, let's denote this is the approximation of this is the approximation to this. T1 would be the approximation to this, right? So how do you find an approximation? So you can write a Taylor expansion around t naught, right? So let's write that down. So x of t, you can write the Taylor expansion, right, which is an infinite series, right? Do you remember that? Yep, the k derivative evaluated at x t naught, right? T naught divided by factorial k and t minus t naught to the power k, right? So this is an infinite series, right? So this series converges to this function on a certain interval. We know that, right? So if you truncate this infinite series from somewhere, right, so you can find an approximation to that, right? So basically we want to find an approximation of value at this point, then you can substitute this point into here, this expression. When you substitute this, the left hand side becomes this x of t naught plus h, right? And the right hand side becomes, so this is your first term and second term. So you know the difference between these two is h. H time first derivative of x evaluated at t0 divided by factorial 1, which is 1, right? And the second term would be this h squared and second derivative evaluated at t0 divided by factorial 2, and this goes on, right? This is an infinite series. You get this one, right? So this one is the Taylor expansion. So if you cut down that expansion from somewhere, or you ignore the, so suppose you ignore all terms from here, you get rid of all terms from here, so you don't write, then you can get an approximation. This is the approximation. So this is your approximation. This is your, according to our notation, this is your x sub 1, right? So this is an approximation to this function x evaluated at t1, right? So this is an approximation to this, right? Definitely you can find the error, right? You know how to find that. So because this is the Taylor polynomial, difference between, this is the exact and this is the approximation to that, the difference between these two gives you the error. So error would be h to the m plus 1, because you cut down all the terms from here, right? You throw away all terms of the Taylor expansion from here, right? From here. So that's why you get this order. The error of the order is this: h to the power m plus 1 times m plus 1 derivative of psi. Psi is a number in between t0 and t1, right? So in between t0 and t1, psi is located somewhere here, right? All right, so that is psi. So this is your error when you use the Taylor. So this is an approximation to that, this one, right? So when you approximate the unknown function using Taylor polynomial, you get this much error. The order of error is m plus 1, right? Okay, let's consider this case, m equals 1. First order Taylor polynomial. First order, yep. This is called a first order Taylor series method. This is called first order Taylor series. Taylor series method, right? First order. That means you throw all the terms you throw away all the terms of that infinite series from here. So you don't consider these terms. You just consider the first two terms of the Taylor expansion, right? You look at this. So x naught is, yep, this one. Let's denote, this is x naught and plus h time f x prime evaluated at t naught, right? This one, h time x prime evaluated at t naught. So you throw all these terms away, right? Alright, you don't consider. So this is called first order Taylor series method, right? Alright, so yeah, and we can give a special name, and this is also called forward Euler method, right? When m is equal to 1, in this case we call forward Euler method, right? So if you know this one, right, so you know the initial condition, right? So x is unknown function, so we start off from here. So this is your we know this value x naught, right? So using this we can find x1, right? Again you can find this, you can find an approximation at this point as well, right? X2, and we can carry this out, right? We can carry on this method, we can proceed, we can continue this method, right? Like this, right? So this is the k step, right? If we know k value of k approximation value of x function at tk, right? All right, if you know the value of unknown function at tk, this is an approximation value, right? Then using this formula you can find an approximation at this point. Something like, yep, x k plus 1 here. If you look at this formula, if you know an approximation value at tk, then you can just plug this number into here. Then by plugging this number into here, you can find the next iterative, next approximation. So this is the next approximation at tk plus 1, right? So this is the first order Taylor series method. So if you look at the second order Taylor series, this is called second order Taylor series method when m is equal to 2, right? So now we consider only these three terms of the Taylor expansion. We throw away rest of terms, right? So here, look at this. This is the first term, second term, and third term. So we can write this one, this x double prime, in terms of so basically this is our problem, right? X prime is f, and we can write f prime in terms of f double prime in terms of f. In this way, definitely here, look at this, f double prime is equal to first derivative of x prime, right? So you know that x prime is equal to, here look at this, f of t comma x, right? So yep, the first derivative, take the derivative of this one. X prime is this, f of t comma x. You know x is a function of t. So if you want to find the derivative of this one, you have to use chain rule. Let's use chain rule. Using chain rule, this one is equal to this, right? What is the chain rule if you don't remember? So chain rule would be, yep, f is a function of yep, t and x, and this one is a function of, yep, t. Yep, x and t are function of t. Then dy by dx yep, df by dt, right, is equal to what? D, yep, f, the derivative of f with respect to t, the derivative of f with respect to t, and the derivative of t with respect to t, which is 1. That's why you get this. And next one, I will use another color. The derivative of f with respect to x, which is this, and the derivative of x with respect to t, which is x prime, because x is a function of single variable t, right? That's why you get x prime. So you know x prime is equal to f, then sub that, then you get this. Then you can substitute this value here, x double prime is equal to this. You can sub this thing, this whole thing, entire thing into here, right? Then you get something like this. x1 is equal to x naught plus h times f evaluated at t naught and x naught, right? So because x prime is f, x prime is f of t comma x, so the function value at t naught is f of t naught comma x naught, right, plus 1/2 h squared, and plug this in, right, plug this in, right, this one. So this one is the second order, yep, m equals 2 case, yep, this one is called the second order Taylor method, series method, yep. So you can write, in general you can write this k plus 1 if you found an approximation of x at tk, then you can find the next iterative, you can find an approximation at tk plus 1, which is this, right? I hope you understand. So this is the general form, right? So do you know the procedure? So here, so we start off from here. This is your t naught, right? So this is the initial condition, x naught, right? So this is given, so we know this value. So this is x is an unknown function. First you discretize your t, dependent t, right? So t1, t2, t3, and let's say this is your tn final, t final, yep, last point, right? So we know this initial condition. Using this initial condition here, look at this. So throw this initial condition into the equation and t naught as well. You can find x1, an approximation value. This is an approximation value at t1. Using this, you can find x2. This is an approximation value. So x2 is an approximation value of value of t2. Yep, at x2 is an approximation value of x of t2, right? And we keep going like this. We keep doing this until you get the last point. And right now f and f capital, yep, f capital, yep. I hope you understand this Taylor series method. So this is the general method of order m. So first order one is called, we give a special name, which is Euler, forward Euler method, and this one when m is equal to 2, this is called second order Taylor series method, which is this one. Also you can consider third order by considering first 1 2 3 4 first four terms of the Taylor expansion. So by considering first four terms of the Taylor expansion, you get third order Taylor series approximation. These are approximation values, right? To these, yep. Xk, if you write, yep. Xk is an approximation value to x of tk. Right, hope you understood Taylor series method. In my next video, I hope to discuss more example related to Taylor series method. Right?